Section 1. The Big Bang, Genesis Unveiled. Picture this. A universe in its infancy, smaller than an atom, unimaginably hot and dense, then bang! The Big Bang erupts, not with a sound, but with an expansion so rapid and profound that it sets the stage for everything we know. Stars, galaxies, planets, even you and I owe our existence to this singular event. But what triggered this cosmic explosion? What secrets lie hidden within those first fleeting moments of creation? The Big Bang, despite its name, is more of a mystery novel than a straightforward tale. It's a puzzle with pieces scattered across the cosmos waiting for us to find and assemble. Fortunately, scientists have been hard at work, piecing together the clues and developing theories that explain the universe's birth. It's a journey that takes us to the very edge of our understanding, where the known universe meets the vast unknown. So, buckle up as we embark on this thrilling exploration of the Big Bang, where we'll delve into the heart of the cosmos and uncover the secrets that have captivated humankind for millennia. Section 2. A universe smaller than an atom. Imagine a time when the entire universe, everything we see and know, was crammed into a space smaller than a tiny atom. It's almost impossible to fathom, yet that's the mind-blowing reality of the Big Bang's starting point. This primordial soup wasn't made of atoms as we know them. Instead, it was a chaotic sea of energy and exotic particles. Think of it like a pressure cooker brimming with unimaginable energy. Temperatures soared to levels that dwarf even the hottest stars. The laws of physics as we understand them today break down in this extreme environment. It's a realm where our current theories struggle to hold. But from this chaotic inferno, something incredible emerged. As the universe expanded and cooled, energy began to transform into matter. This wasn't your everyday transformation. This was E=mc2 in action on a cosmic scale. Einstein's famous equation that demonstrates the interchangeability of energy and matter. This primordial soup didn't contain the diversity of elements we see today. It was primarily a sea of fundamental particles, quarks, leptons, and their antimatter counterparts, constantly colliding and annihilating each other in a cosmic dance of creation and destruction. It's from this chaotic beginning that the universe as we know it began to take shape. Section 3. Cosmic Inflation, Expanding at Warp Speed. The Big Bang wasn't just an explosion, it was an explosion on fast forward, expanding faster than the speed of light. This period of hyperexpansion, known as cosmic inflation, lasted for just a fraction of a second, but its impact on the universe was monumental. Imagine a balloon with dots drawn on its surface. Now, imagine inflating that balloon at an unimaginable speed. The dots representing galaxies would race away from each other, just as they do in our expanding universe. That's cosmic inflation in a nutshell. But why is inflation so important? For one, it explains why the universe looks remarkably uniform in all directions. Think about it. If the universe expanded gradually, we'd expect to see variations in temperature and density. But thanks to inflation, everything was spread out evenly, like dough flattening in a pizza pan. Inflation also solves the horizon problem, which puzzled cosmologists for decades. This problem arises from the fact that distant regions of the universe, which shouldn't have had time to communicate with each other, appear remarkably similar. Inflation provides an elegant solution. These regions were once in close contact before being rapidly pushed apart. Section 4. The first elements, hydrogen's reign. As the universe continued to expand and cool, the stage was set for the formation of the first elements. Remember that primordial soup of particles? As temperatures dropped, those particles began to slow down, like dancers pairing up at the end of a waltz. Protons and neutrons, the building blocks of atomic nuclei, could finally stick together, forming the simplest and most abundant element in the universe: hydrogen. It was a hydrogen-dominated universe with a smattering of helium and trace amounts of lithium. Think of it like a giant cosmic kitchen. The intense heat of the Big Bang had finally cooled enough for the simplest recipes to come together. These first elements, forged in the crucible of the early universe, would become the raw ingredients for everything else we see in the cosmos. But how did we get from a universe filled with mostly hydrogen to one with the incredible diversity of elements we see today? That's where stars come in, acting as giant cosmic furnaces, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron. Section 5. From soup to stars, gravity takes charge. In the aftermath of the Big Bang, the universe was far from uniform. Tiny quantum fluctuations amplified by inflation created regions of slightly higher density. These denser regions possessed a little extra gravitational pull, drawing in surrounding matter like cosmic vacuum cleaners. Over billions of years, gravity sculpted these clumps of matter into vast cosmic structures. Gas clouds collapsed under their own weight, igniting to form the first stars, brilliant beacons illuminating the early universe. These stars were true pioneers, their light piercing the darkness and setting in motion a chain reaction of cosmic evolution. These first stars were massive and short-lived, burning through their fuel quickly and ending their lives in spectacular supernova explosions. These explosions, while cataclysmic, were essential for seeding the universe with the building blocks of planets and life. As Carl Sagan famously said, "We are star stuff." The very elements that make up our bodies, the carbon in our cells, the oxygen we breathe, were forged in the hearts of stars and scattered across the cosmos by their explosive deaths. Section 6: Dark Matter, the universe's invisible hand. As astronomers peered deeper into the cosmos, they stumbled upon a perplexing mystery. Galaxies were spinning much faster than they should have been, given the amount of visible matter they contained. It was like watching a merry-go-round spinning at breakneck speed without flinging its riders off. The only explanation? There must be something else out there, something invisible, providing the extra gravity needed to hold these galaxies together. This mysterious substance, which doesn't emit, absorb, or reflect light, became known as dark matter. Imagine a shadow puppet show. We see the shadows cast by the puppets, but we can't see the puppets themselves. Similarly, we can't see dark matter directly, but we can infer its presence by its gravitational effects on visible matter. Dark matter accounts for roughly 85% of the matter in the universe, dwarfing the familiar atoms that make up everything we see. Its exact nature remains one of the biggest unsolved mysteries in modern astrophysics, a tantalizing enigma that continues to captivate scientists today. Section 7: The Expanding Universe, a Cosmic Balloon. Imagine dots scattered across the surface of a balloon. As you inflate the balloon, the dots move farther apart from each other. That's a simple analogy for the expanding universe. But here's the kicker. In the cosmic balloon, there's no center, and every point appears to be expanding away from every other point. This expansion isn't like an explosion where debris is flung outward into pre-existing space. It's the very fabric of space-time itself that's stretching, carrying galaxies along for the ride, like ships on the cosmic ocean. The expansion of the universe was one of the most profound discoveries of the 20th century, overturning the long-held view of a static and unchanging cosmos. It implies that the universe we see today was once much smaller and denser, lending further support to the Big Bang theory. But the story doesn't end there. Astronomers have discovered that the expansion of the universe is actually accelerating, driven by a mysterious force dubbed dark energy. It's as if someone is constantly adding more air to our cosmic balloon, causing the expansion to speed up. Section 8: Echoes of the Big Bang, the Cosmic Microwave Background. Imagine tuning your radio between stations and hearing a faint hiss. That hiss, present everywhere in the sky, is the Cosmic Microwave Background, or CMB, the faint afterglow of the Big Bang. It's a relic from a time when the universe was a mere 380,000 years old, long before stars and galaxies even existed. In the early universe, things were so hot and dense that atoms couldn't even form. Instead, electrons and protons zipped around freely, constantly colliding with photons, the particles that make up light. This created a dense, opaque fog that prevented light from traveling freely. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, a process known as recombination. This event cleared the cosmic fog, allowing photons to stream freely for the first time. Those ancient photons, stretched out over billions of years by the universe's expansion, now make up the CMB. The CMB is a treasure trove of information about the early universe, providing a snapshot of conditions when the cosmos was in its infancy. Its discovery in 1964 revolutionized cosmology, providing the most compelling evidence yet for the Big Bang theory. Section 9: The Ongoing Quest, Unraveling Cosmic Mysteries. Despite the remarkable progress made in understanding the Big Bang, many mysteries remain. What exactly happened in the first fraction of a second after the Big Bang? What is the nature of dark matter and dark energy, which together make up 95% of the universe's energy density? These are just a few of the questions that continue to drive cosmological research. Scientists are constantly pushing the boundaries of knowledge, developing new telescopes, instruments, and theories to probe the universe's deepest secrets. The Large Hadron Collider, the world's most powerful particle accelerator, is recreating the extreme conditions of the early universe, searching for clues about the fundamental forces that govern the cosmos. Space telescopes like Hubble and James Webb are peering deep into the universe's past, capturing light from the first stars and galaxies. The quest to understand the Big Bang is a journey of discovery, a testament to human curiosity and our innate desire to comprehend the vast and mysterious universe we inhabit. Section 10. The Big Bang's Legacy, Our Place in the Cosmos. The Big Bang is more than just a scientific theory. It's a story about our origins, a grand narrative that connects us to the cosmos in a profound way. It tells us that we are all products of the same cosmic event, forged from the ashes of stars that lived and died billions of years ago. The Big Bang reminds us of the vastness of the universe and the incredible journey that matter and energy have taken to create the world we see today. It's a humbling realization that we are but a small part of something much greater than ourselves. But it's also an empowering thought. We are star stuff, capable of contemplating its own origins, unraveling the mysteries of the universe, and pushing the boundaries of human knowledge. Section 11. Our cosmic journey continues. The story of the Big Bang is far from over. It's an ongoing saga, with new chapters being written all the time. As we delve deeper into the cosmos, we're sure to uncover even more surprises, challenging our assumptions and expanding our understanding of the universe. So keep looking up at the night sky with wonder and curiosity. Every star you see, every galaxy you glimpse, is a testament to the awe-inspiring power of the Big Bang, a cosmic event that shaped the universe we know and love. Our cosmic journey continues,